Okay, now people, let me teach you the rules. After we've done that thing, let's teach you the rules. We have done with the first part of the rules, which is drawing the structures. But now we have to do secondary structure, second rules. So rule number 1, when dealing with bending stresses. Rule number 1, very important. Always, I'm not good in English, but always identify forces and categorize them. That is rule number 1. Rule number 2, this is technical approach, by the way. So technical approach means whatever way, even if you don't understand, that means you can still get the answer if you use this approach. So number 1, always identify forces and categorize them. Then number 2, remember this rule number 1 applies after you have drawn your structure, right? But always, yeah, you will see with an example. And then after identifying the forces and categorizing them, then you go to the next step. What is next step? If there is direct stress, do it. And the formula for direct stress is just F over area. And this area, cross-sectional area. Force, whatever force it may be. So if you have a force that causes direct stress, you identify it and then force over area. How is the direct stress? For example, if we have a cross-sectional area like this, and then we have a force that is parallel or perpendicular to it, to this cross-section, that is a direct stress. Every time the force is parallel, perpendicular to the cross-section, so we have something like this. Let's say we have a beam. We have something like this. I don't know if you see. Forgot. If you have a beam like this, and then you have axial force, and then you can see this force is perpendicular to the cross section, then this force causes direct stress. Same thing if you have a column. If you have a column like this, and then you have a force that is going up, this force causes a direct stress on this one, right? So always identify those forces and then you write them and then you draw a graph. Remember, the graph is always going to be AB, neutral axis. You're going to see with an example. Then rule 3, bending stress. If there's a force that causes bending stress, that means you have a beam like this, and then there's a UDL on top of this, and then let's say the structure is simple supported. Yeah, even this side is simple supported, and then this force causes what? Causes bending on the neutral axis. So we have a neutral axis here, and then you have AB, and then whatever. You see, this forces causes bending, and then bending has, in this case, have compression and have tension. So there's bending, there's compression. That means this side is going down, this side is stretching. So you have a stress that is compressing, stress that is tensile. Yeah, on this cross section. Every time when you have a bending stress, you always gonna have these two. Every time there's bending stress, you just always know that you have compression, also tension. Always. Don't make that mistake of always when you have a bending stress, whatever force that causes that bending stress, you always this. Always, there are always gonna be two like this, always. Then basically, after that, you can just rule 4. You can just also after doing this, you draw your AP. Most of the time for a direct stress, AP is just one thing. If it's compression, let's say compression is going up, and then for bending stress, it's always gonna like a butterfly thing or whatever. So you have, let's say for compression, that means the top one, yeah, and then bottom one. Does not matter now, since we are not doing an example, I'm just highlighting. You'll see in time what do I mean about these things. Then rule 4. Then resultant. After you draw these structures, you can just write AP again, and then you just add. Compression is always negative, so this plus this is gonna give you a bigger this, and then you go to the middle. You always start with the A, the maximum, go to the middle. So you know from here, the middle is 0 plus this. You know exactly if this is your previous neutral section. You see 0 plus this, you know, okay, this thing has shifted up. Then this and this is more down, and then you just join the lines. No, excuse my drawing, but you can see there's a shift here. So there's your new, you can say it prime. This is your new neutral axis. If you want to calculate this neutral axis, you see this, we have this triangle, and then we have this smaller triangle. Then you can use similars. You can use this stress over this stress equal to this over this, this length over this length, up to you, but you're gonna see the example. So resultant stress distribution, this is how we do this first, this plus this, this plus this, and then from there you can just pick up what is your mean and what is your max. From here you can just say, okay, this is your max and it's compression, this is your minimum and it's tension. Simple, ne? Okay, let's continue now. Let's do an example so that you can let's highlight now. Let's highlight step 1, identifying forces. Right? If you are given density or any force over something, let's say over meter squared, force over meter cube, force over m. If you are given something this just know this is synonymous with UDL. So it's congruent, meaning what? If you are given density or force over area or force over meter cube, or pressure like actual pressure in kilopascals, mpk. Remember, pressure is always parallel to the perpendicular to the surface. So if you are giving this and this and this, just note you are actually giving a UDL. Yeah, right. But we have to take note of density depending on how you see it. But just note, if you are giving density, force over area, force of this, you are actually giving UDL. Okay, so this is step 1. How do we categorize forces? You need to know if you are given density, you did UDL. If you are given pressure, UDL. Force over area, UDL. And it depends where this force acts. So for example, if this density is throughout the surface, then you can assume this is UDL, then you're gonna cause bending stress. Yeah. And then what else do we have? Pressure. Okay, anything else we're gonna see it with example. For now, yeah, for now it's just highlighting what we're gonna go through, right? Okay, here's a problem here. It's taken from Drostky chapter 10. So if you have that book, just look at it, 10.8. So the question goes like this: a timber beam of what, 150 wide and 300 millimeters deep has an effective span of 4,8. The density of the timber is 490 kg per meter cube. Calculate the point load and the beam can carry at the center of its span if the stress in the timber is not to exceed 41, MPa. The mass of the beam must be taken into consideration. Right, let's analyze line by line. So here we are given a timber beam of 150 wide and 300 deep. That means this is, from here, this is a rectangular shape. So we know the cross section is rectangle, so we can just draw it down. So we have this cross sectional area. Okay, I'm gonna write it with my, so we have what, 150 mean wide, that means 150 is here, millimeters, and then we have 300 millimeters here, right? You have something like this. Then has an effective span of 4,8. Remember, this is a beam, so a beam, let's just write it here. We have this thing, something like this, and then we have 4,8 its length, right? And then, so according to the question, you are not told if it's simple supported or whatever, but we're gonna assume, for now, let's assume simple supported. So we can have RL, RR here, and then we have 40,8 meters, right? Remember, this is a beam and this is its cross section, beam cross section. So I don't want to draw something big and then you see, not an artist. Okay, let's go. Then the density of the beam, we are given the density. Okay, it's fine. And then what else are we given? Nothing. So we are given density. Right, and then they say calculate the point load the beam can carry. So we have this beam with this cross-sectional area, and then we are asked to calculate a point load. So a point load, and then where is it? At the center of its span. So at the center, they are saying this point load, let's call it BW, capital letter W, right? And then from here, so we have this information, and then so they're saying if the stress in the timber is not to exceed 4,1 MPa. So they're actually talking about bending stress. Why? Because we have only W, and then W only causes bending stress. Okay, it has not to exceed 4,15. And then they say the mass of the beam must be taken into consideration, right? As I said previously, when you see density, it's synonymous with UDL. So in this case, they say the mass, obvious density will give you the mass, because density is what, kg per meter cube. And then the beam is like this. If the beam was like this, the density will be concentrated in one point in the centroid, but the beam is like this, so the density is throughout. That means this thing is causing a UDL. If the density was, if the beam was a column, this is a column by the way, then the density will be just one force here at the centroid. But here we don't have a specific point, that's why it's a UDL. beam, it's a UDL. Column, the weight, it's a weight, and then it's concentrated in the centroid. So in this case, we are given a beam. Then we know exactly this density spread throughout. So this is my structure, all right? According to the previous video, we need to first identify AB. And then another video we said we need to, rule 1, always identify the forces, right? In order for you not to get confused, let's just do it step by step, right? So we have already drawn the structure. We have this force, and then we can, let's say, W1, the UDL caused by this density. We have W1, W2. So by analyzing the force, you can see that they are causing the bending stress. So now, actually, we need to a bending stress. So okay, now we know it's okay. We are dealing with the bending stress using the force, and then on our shape here, we can write these forces. You see, they are coming up. So we have this W big, and then we also have a small W1. So we have something like this. These forces are coming down like this. And then what did we say here? We said, where is this example? We said W or whatever force is always parallel to AB. So from these forces, two forces, we can safely assume this is AB. Based on this force is parallel to this line, is parallel to this line. So AB, you can even write AB here, it does not matter, but choose one thing. So AB is this, AB is that. It's fine, right? Done with AB. And then after AB, Y1 and Y2, right? Yeah, then now draw a neutral axis and then say Y1, Y2. Simple, right? Then after that, obviously we know it's easy. It's IXX, it's XX. You can call it XX, right? Then after that, we need to know where is the part that is compression and tension. So here's my rubber here. Then when it's simple support. So simple support here, and then there's a force coming down. So it's gonna cause what? Something like this. I don't know if you see. It's gonna cause bending like this. So on this side there will be tension, on this side there will be compression. So we know from A to B there's compression, there's tension. Okay, let's go. I know it's hard to comprehend now, but this is a technical approach. First, we draw the structure according to the question. We draw the cross-sectional according to the question, and then you identify your forces. This is your force, this is my force, and then the forces are doing this, and then you can see this is parallel to this, then we have something like this. Then I have my AB, Y1 and Y2, XX, or if you like neutral axis, but I prefer XX. So we're done. Now the goal now is to find W, to find the forces, especially this. So let's first deal with density. Every time you're given density, you go from density to mass to force to UDL. This is the procedure: density, mass to force to UDL. Sometimes if you are given force over mass, so obviously just go straight to here, depend on the question. So in this case, we're given UDL, so we have 490 over kg, over meter cube. Now how would we go to mass? So we need to cancel this volume. That means we need the volume of this structure. So what is the volume of this structure? So the volume of this structure is area of the base times height. In this case, times length. What is the area of the base? So it's gonna be 150 times 300 times the length, 4,8 times 10 exponent 3. Then we have an answer. Let's see the answer. 150 times 300 times 4,8 exponent 3. Hey, this answer is big. I have this. Okay, it's fine. Times 10 exponent 6 millimeter cube. Oh, we needed meter cube. Then we just can divide by 1000 exponent cube. Aibo, what is happening? Let's just do this. 0.5 times 0.3 times 4,8. So basically this is equal to 0,216 meter cube. Convention is anyone games. Then this is my volume, so times 0,216. Then the mass is gonna be 490 times 0,216. The mass is 110,54 kg. And then from the mass, you need to go convert into a force. How do we convert it to force? It's that simple. So force is equal to 105. So this is mass. Excuse my writing. Then force is this times 9,81, which is equal to 1038,2904. And then UDL. So in this case, my UDL is W1. So W1 is equal to 1038,2904. Remember, UDL is what? Force over meters. So now we have forces in Newton, and then you can divide this by the span. Which is equal to 216,3105 Newton per meter. So this is my W1. Then I can just update here 216,3105 Newton per meter. Excuse my writing, but if you listen, you will see. Okay, now let's continue. Now we have find the UDL. Remember, every time you're given density, you must always convert into this. Then we have to find y1 and y2. Remember, the aim is to we want to w, but y1 and y, we need to first find y1 and y2. So every time dealing with bending stress, the first thing is to find your y. So y1, according to this is a rectangle that we know that y1 is equal to y2. And then in this case, is 300 over 2, which is what? 150 millimeters. And then another thing, we have to find its moment, maximum moment of the structure. How do we find the maximum moment? Let's calculate the moment. The maximum, if it was a simple support structure, the maximum moment is here in the center. So we have W and you have UDL. So we know that for maximum at the center for a simple support, you can use this formula, W L squared over 8 if it's a UDL, or W L over 4 for the force, for only simple support. So in this case, we have a force at the same time we have this. So we have a force W times L over 4, and you have a UDL. You can just add. Then what is my W? It's just W. What is my L? 4,8 meters over 4 plus W2 216,305 times 4,8 squared over 8. Then you can simplify this thing. 1.2 big W plus 622,97425. So we have the M, which is like this, and then from there we need an I. You remember the bending stress formula is this. So we need one, we have this, and then we need an I. And then what is my I? I is just thick. So if you are given, remember, I is what? Moment of inertia apart whatever line that separates y1 and y2. So in this case, we have y1 and y2, they are separated by what? Xx. So this is Ixx. And then we always gonna cube the thing, that the line that is parallel to AB. So in this case, the parallel line is 300. So it's gonna be 300 cube times over 12 times what? 1/5. The formula for rectangular is just B cube H. I don't know, it depends. So yeah, which is equal to this 300 cube times 150 divided by 12. So let's try 300 cube times 150 divided by 12. So we have 337,5 times 10 exponent 6 mm4. So we have something like this. We have this. Yeah, pretty much we have everything. Now we love to calculate the bending stress. Remember, y1 and y2, they are same. So according to this, y1 is what? Compression. So, but y1 and y2, they are the same. We can just write it in simple way. Tension, compression is equal to m y over I. So y1 and y2 are the same. Remember, y1 is equal to y2, which is equal to y, which is equal to 1/5. There's no need to repeat this thing. So I have m. What is my m? 1.2 W. 1.2 W plus 6, 2. Let's just simplify this thing to 6,3 in bracket times my W 150. Remember, I'm calculating stress. Millimeters, I'm working with millimeters. Let's not confuse this thing, because when we calculated the UDL, we didn't convert. So let's just convert times 10 exponent. Let me just write it clear. 150 times 10 exponent -3 over, convert also this. So 3 7,5 exponent -6 divided by 1000 exponent -4. So we have something like this. 3, 7, 7. There's something wrong here. Oh, 3,37, 5 exponent 6. Then you divide it by 1000 exponent 4. I was doing the mistake. So we have 3,375. Because I already said divide. If I said multiply, I was supposed to say multiply. This is, yeah, meter 4. And then you have your answer here. Right, since we have this unknown, it's better to make this one a subject of the formula. Remember, when you draw a graph, you're gonna have AB, and then neutral axis, gonna have tension, have compression. According to the question, they say the timber should not exceed 4,1 MPa. So we have something like this. So at this end, either tension is what? 4,1 MPa. Also here, remember Y1 and Y2, they are the same. So it's better to assume both of them they are equal. Compression, tension here. So this is the maximum, this is the maximum. And the question says it should not exceed. So obvious, if this is the maximum, that means it should not exceed this 4,1. So since tension and compression are the same and Y1 and the Y1, you can safely assume that 4,1 times 10 exponent 6 is equal to 12, W plus 623 times 150 over this. Then you can just solve for W. Remember bracket. Then we have something like this. So we have 9225 is equal to 1.2 W plus 623. So we have 8602 is equal to 1.2 W. Then W is equal to 7168,33 Newton. So the force that this can carry is what? Can convert it further to be 7,17 kilonewton. So it's 7,17 kilonewton. So this is a technical approach. There are easiest method when you are using formulas. This is a technical approach when you start by structuring and analyzing. So obvious, this is the first video. It's clumsy, whatever. I don't really care as long as you get the concept.